I'm Yejia, and I feel so excited to be here to introduce the low-dimensional classifier and our related work, the MetaLDC, for fast on-device adaptation. So I would like to start with giving some context about the work before we officially get started about the MetaLDC. So the first concept I want to introduce is the vector symbolic architecture. So it's also called the hyperdimensional computing. So as we all know, the deep neural networks have achieved many remarkable successes in recent years in many areas, such as the computer vision, the NLP. And on the other hand, there is a traditional symbolic AI. For the deep neural networks, so the main focus of it is to learn a meaningful representation for objects. However, they are not able to decompose joint representations to obtain distinct objects. Namely, they suffer from the binding problems. On the other hand, in the traditional symbolic AI, the representation is usually handcrafted through formal logic or some rules, and they can be then used to reasoning or make some decisions. And compared to the DNNs, they have better interpretability. And on our belief, we think that the VSA can serve as a common language, the bridge between the neural network and the traditional symbolic AI. As I mentioned before, the VSA can also be called as a hyperdimensional computing. The hyperdimensional computing, it would map the objects, the features and the values of the object into a very high dimensional space. The very high dimensional space vectors are usually composed of bipolar values, namely the zeros and ones. And then these vectors can be computed in a quite efficient ways by the hardware, like the Hamarad products or the dot products or the additions. At a very high level, the advantages of the HDC can be summarized as a few. First, because the information is distributed in a quite highly distributed manner, each bit or a feature in a high-dimensional vector space contributes to the overall representation. This allows for more efficient storage and the retrieval of the information. Meanwhile, the HDC is quite highly robust to noise and errors in data because the information is distributed in the entire high-dimensional vectors. This means that even if some bits of the vectors are corrupted, the overall representation can still be recovered and also generates similar accuracy as is not corrupted before. Next, I want to introduce the non-dimensional classifier, which also serves as the backbone of our method. Compared to the HDC, the LDC has very low dimensional spaces because although the HDC has a very high efficiency on the hardware and also a robustness against the random bit errors, but it can bring about a large model size because the vector space are usually quite high dimensional, from 8,000 to tens of thousands. In contrast, LDC only use like tens of dimensional to represent the vectors, and at the same time, it can achieve higher accuracy compared to the HDC by a systematic training way. If you look at the figure, the LDC are composed of three components: the value box, the feature layer, and followed by a class layer. The value mapping, the value box, it would map the objects, the feature values of the object into a bipolar value. It's a very sparse BNN network, the binary neural network. And for that is a feature layer. So the feature layer would bind the features and the values together. at the end, the class layer would just output the similarity scores for each dimensional space. So because as we know in the DNN, the last class layer also compares the distance between different vectors. So similarly here, the class layer would also use the cosine similarities to compute a similarity score between different vectors and get the class results for each object. So here, I would like to introduce our work, the MetaLDC framework. So the goal of our work is to enable the LDC to fast adaptation on different tasks on heterogeneous tiny devices. So the motivation is that if we train a single LDC for each tiny devices, it can be quite labor intensive. Also, the tiny devices usually have limited computational resources. The backpropagation and the gradient updates are quite expensive for them. So we therefore propose a MetaLDC method, a LDC-based method for tiny devices. So in a nutshell, it would pre-train a LDC classifier by learning from different but related tasks. And then the obtained initialization would be used to adapt to different tasks on a new devices. So if you look at the right part of this figure, so in the fast adaptation stage, the formal layers would be frozen during the adaptation stage, but we just fine-tune the last layer using a few examples from the new tasks. So sorry, it's a bit complicated here, the algorithm. But the algorithm is actually just a different version, maybe a minor revised version compared to the standard MAMO algorithms. So in the training stage, the algorithm would first train on a set of meta-training tasks. For each task, the model would be initialized with a set of parameters and train a small amount of data from the task. The gradient of the loss function with respect to the model parameters would be computed and used in a way to maximize the expected performance across all tasks. So you can see there are two loops in the algorithm. So on the inner loop of the algorithm, we would only update the last layer's parameters. So we treat the last layer of the parameters as a specific task embeddings. And on the outer layer, we would update all the parameters to minimize the loss of objective functions. On the fast adaptation stage, we would fix the formal layers of the LDC, but we just update the last layer of the learned initialization. And to further reduce the cost of the computation, we would manually compute the last layer's gradients and feed these gradients into the hardware devices to further reduce the complexity of the computation. One thing worth noting that in the training part, we can train that initialization on a GPU space. But after training for the fast adaptation for different tasks, we can use that on a CPU because we only need to update the last layers. And the gradients of the last layer is also manually computed through the hinge loss. I would quickly introduce some setup for our experiments. So we use two data sets in our experiments. One is the rotated MLIs, another one is the split isolate. So for the MLIs, the training data, we rotate the MLIs images from the degree between the range of 10 to 20 degrees. And for the testing data, we have 5 tasks. The task of each rotation degree is from 0 to 8. And for split isolate, so because in total the UC isolate data sets has 25 classes, we would use the first 20 classes as the training data sets, and each of them we would sample 4 classes from it. And for the test data sets, the test data sets is sampled from the remaining 5 classes, and each task with 4 unique classes as a testing data set to test the performance. As for the baselines in our work, we use 3 baselines. One is a pre-trained LDC. So the pre-trained LDC just uses standard supervised learning to train the LDC classifier. But in the fast adaptation stage, we also update the last layer to test its performance. Another one is called the MetaLDC full. So MetaLDC full uses exactly the same training algorithm as I showed before, but on the evaluation stage, when it fast adapts to the new tasks, we would fine-tune all the layers rather than the last layer. And the last one is the HDC with the training. So the HDC with the training is a hyperdimensional classifier, but we would retrain the HDC classifier if there are errors in the training process. Next, I would like to present some key results of our work. So, as highlighted by the red and the blue color here, you can see our MetaLDC outperformed other methods in the evaluation tasks. We also want to present our inference cost. So you can see our MetaLDC has achieved much smaller model size compared to HDC, and also much less latency and energy compared to the HDC method. And the evaluation is done on the FPGA platform. We also test robustness against the hardware bit errors of our method because, as we mentioned before, the HDC is quite robust to the hardware bit errors. But as you can see, our MetaLDC also achieved quite a high hardware robustness, and it's even better improved compared to the HDC. I think that's because in the training process, we learned a better generalization from different but related tasks, so it enables better robustness compared to the original LDC method. We also do some additional analysis. So we just use the repetition learned from our training process and test that on the data sets. And we found out the MetaLDC non-fully trained method also has closer performance to the full MetaLDC. So we want to use these figures have shown that our training algorithm has truly learned a useful initialization. So here is just some summaries and takeaways. So based on our empirical results, we can see that the MetaLDC can fast adapt to unseen tasks by interleaving meta training for resource-constrained tiny devices. And our empirical results have also shown that the MetaLDC has achieved better accuracy and efficiency compared to the HDC models. Thank you for giving me the opportunity to present here, and I'm happy to take any questions.
Okay, thank you very much.